Spatial data converters need artificial intelligence. Welcome to this video in which I, Georgi Radulov, will talk about the emerging needs for artificial intelligence in the area of data converters and what we can do to accommodate artificial intelligence in our data converters. Artificial intelligence is already penetrating our lives as part of the technological progress of human society. This progress made possible humans to fly better than eagles with our airplanes, to move faster than cheetahs with our cars. So, can we exceed ourselves? Can we think better than humans? Let's take a look at the artificial intelligence and what we can do with it. We already benefit from the artificial intelligence thanks to the software and the computational power of our computers. Through artificial intelligence, we reconstructed a photo of a black hole 500 million trillion kilometers away. Artificial intelligence is widely used in pattern recognition in medical ultrasound to diagnose various diseases. Artificial intelligence enables safe driving cars. To benefit from the artificial intelligence, however, we need to provide the needed hardware. We need to provide the environment in which we can get the benefit from it. Think about sufficient redundancy in our hardware, flexibility and integration to keep the performance at the top level. How can we adapt our hardware to enable artificial intelligence at lower implementational levels so that we benefit not only at software level? In the following slides, I would like to consider the emerging needs of artificial intelligence in the area of data converters, analog to digital converters, digital to analog converters, wireless transmitters and receivers. The key enabling feature for various future application and central application for my talk is the spatial discrimination, which should come next to the temporal signal discrimination used in the traditional signal processing. We will see that it requires arrays of data converters, which poses challenges of complexity, area and power consumption. I will start at system level by considering applications for which we must enable spatial selectivity and descend to the components and circuits. I will present our novel beamforming sigma delta modulator, which can be used in a hybrid phased array receiver. Then I will consider several examples of self-calibrating digital to analog converters, which can be used in the phased array transmitters. What these examples illustrate is how on-chip intelligence can organize the complexity, relax the design requirements, and save resources. So there is this video in YouTube which shows a nearest case. A child crosses the street, an incoming truck manages to just stop and avoid the worst. So, see it. Yeah. In the net, there are discussions if their automatic emergency braking has been involved. It turns out that we should thank the reactions of the truck driver. The main arguments on why there was no automatic emergency brake in this particular case are that the child is simply a very small target to detect, and it appears from the shadow of the green bus. Luckily, the driver could have accounted for such a possibility and the reactions were just okay. However, we need to take the lessons from this and design our cars so that we do not rely on humans to save human lives. We need reliable radars supported by reliable artificial intelligence to make decisions. PMCW radar is the so-called digital radar that features robustness but imposes tougher design requirements on its building components. It is an example of a communication channel. The radar sends a string of data, it reflects and gets detected back by the receiver of the radar. Thus, it is very much like a modern communication system with a transmitter and a receiver, provided that we solve the challenge of the spatial selectivity. We must be able to send a spatially directed data in order to locate our target or a communicating party. There will be many interferers, and we should be able to distinguish between our targets and interferers. Forming such a spatially directed beam is already possible today. Our next step should be to form multiple simultaneous beams. In the context of the communication systems, this means that we will be able to communicate with multiple users in the same time and in the same frequency. To form and use multiple beams, we need digital beamforming. Let's look at the basic principles of beamforming and how to enable spatial domain signal discrimination. First, for spatial selectivity, we need redundancy of the reception elements. We need an array of antennas. There is a front of an incoming electromagnetic wave. If the front comes to us from the frontal direction and we sample the information at a given point in time, all samples will have the same value. It will be like a static signal if we look along the line of one-dimensional array antennas. Imagine that the EM wave comes at an angle, and the EM waves per antenna propagate different paths. If we sample the front at a given point in time and we look at the samples, then they will be different. There will be an async component along the space. This is what we defined as a spatial frequency, and it is effectively a metric of the angular direction of the target. Using the spatial frequency of the signals, we can discriminate between a target and an interferer. The beamformer will constructively combine all the signals of the target and destructively combine all the signals of the interferer. In this way, the interferer is suppressed and the remaining electronic components do not need to accommodate for it in their dynamic ranges, which results in better linearity and less power consumption. If we perform the function of beamforming at RF domain, we face challenges with the accuracy, the steering, and we are limited only to a single beam, since at the point of beamforming information is lost. An important trend of today's research effort is the digital beamforming. Beamforming in digital domain requires to make the information of every antenna available in the digital domain. There it can be easily copied and multiple beams can be constructed at the same time. This is the most important advantage of digital beamforming, the ability to create multiple beams. Next to this, we have great accuracy and versatility. However, the resources needed to digitize the information from every antenna grow. Not only we have now arrays of mixers, arrays of variable gain amplifiers, and ADC arrays, but all these components need greater dynamic ranges to accommodate all the targets and interferers, which leads to prohibitively large power consumption and cost. To solve this challenge, we research hybrid beamforming methods, in which the beamforming function is split between analog baseband domain and the digital domain. Here I show a novel beamforming sigma delta modulator, which we introduced in the ECCTD conference of this year. The key concept here is that we combine spatial FIR filters and sigma delta modulators. We realize the sigma delta feed-forward coefficients as spatial finite impulse response filters Let's see how it works with a simple example. This is a first order sigma delta modulator which, with a spatial field filter based on 16 antennas. In this example, our target is frontal, that is at 0 degrees, and we have interference at 29 degrees, 49 degrees, and minus 38 degrees. All signals are represented with two tones to emulate overlapping bandwidths. Without a spatial filter at the input, we get the red spectrum. With spatial filter, we get the blue spectrum. We choose the coefficients of the field filter in such a way that a low pass characteristic is realized as shown in the plot. Further, the position of the zeros can be chosen in such a way that the interferers are completely cancelled. We can use several such beamforming sigma delta modulators in an array to form a hybrid beamforming by combining these with digital beamforming. In such a way, we form broad beam through the analog baseband beamforming and narrow beams through the digital beamforming. Here is a generic view of the beamforming sigma delta modulator with multiple feed-forward coefficients realized as spatial filters. Now we need to take care about more things than usual. In other words, the complexity grew. Consider the signal-to-noise ratio, the signal-to-interference ratio, the power consumption of the whole solution. Thus, the choices of the spatial coefficients and the positioning of the zeros are crucial and correlated with other parameters of the sigma delta modulator. Here is the transistor level implementation of our beamforming sigma delta modulator. The spatial filters can be implemented as a bank of resistors, controlled by switches. By programming the coefficients, we can realize the spatial selectivity. In these graphs, various spatial transfers are shown for frontal signals and for targets at the sides. The spatial functions are shown with their ideal analytical characteristics as lines. And as the coefficients are quantized, these are the blue circles. The imperfections due to the implementation lead to incomplete cancellation of the interferers as shown in the spectrum. This reveals the increased complexity when we add the spatial selectivity dimension to the design of a sigma delta modulator. Let's appreciate the challenge of increased complexity now. Here the tuning points of the beam-forming sigma delta modulator are shown. If you tune coefficients, you alter the balance among the components' values. In other words, changing some coefficients for a given function actually affects others. Here I list the interdependencies in the system. We have a tuning for the local spatial coefficients, for cancellation of interference, hierarchical spatial selectivity, the sigma delta modulator, signal transfer function, the noise transfer function, the stability of the sigma delta, the signal to noise and distortion ratio, matching, etc., etc., etc. There are too many parameters. The complexity explodes. And this is a challenge. We believe that the artificial intelligence can help in a very practical way. Artificial intelligence can organize this complexity. The standard self-calibration loop of self-measurement algorithm and self-correction is appended with real-time application information and the use case. We cannot envision all possible options. There must be learning and algorithm updates. Thus, we see the practical route towards the artificial intelligence in the data converters through appending the existing self-calibration methods with self-learning and real-time information. A few observations so far. Thus, we see the artificial intelligence in the mixed signal domain hardware as a solution to the challenge of the increased complexity, requirements, and needed resources of the applications. It can build on the smart, already existing algorithms through self-learning and real-time information, so that artificial intelligence can help us organize complexity, relaxing requirements, and reducing the needed resources. However, we need to adapt our hardware to provide sufficient redundancy, flexibility, and integration for the artificial intelligence to do its job. In the following slides, I would like to show how resources like occupied area can be traded for intelligence. Self-calibration of digital-to-analog converters in the wireless transmitters can lead to smaller sizes, hence better integration and improved performance. Smaller sizes per unit means that we can integrate larger arrays and provide more redundancy and flexibility. We need large arrays for digital beamforming and for redundancy needed by the artificial intelligence. However, massive DAC arrays are possible only if integrated together with the digital processor, where the artificial intelligence will be. If the integration is not on chip but rather on the PCB, there will be huge challenges with power consumption and time synchronization. Thus, we need to integrate the DAC units on chip. We need small, high-performance units. The problem of combining high linearity and small area is matching. High linearity requires small errors. However, the matching errors are reversely proportional to the size of the transistors, as given by the famous formula of Pelgrom about the relative standard deviation of the current generated by a transistor. The bigger the transistor, the smaller the spread of its current. To overcome this limitation, we need smartness. We can measure the errors, process the errors with an algorithm and derive the precise correction. This is self-calibration. Resources can be traded for intelligence. Calibrating the errors of the DACs is key to small area high performance and hence to massive arrays. Let's see how it works. First, let's illustrate very briefly how mismatch errors lead to non-linearity in both extreme types of DAC architectures, the binary and the unary architectures. On the left, the binary DAC architecture is illustrated and how it constructs its output based on scaled binary units. If these units are not exactly the same, there is a severe nonlinearity in the DAC transfer characteristic, particularly in the middle scale. On the right, the unary DAC architecture is illustrated and how it constructs its output based on nominally identical unary units. If these units are not exactly the same, there is milder nonlinearity in the transfer characteristic. Binary architectures are more efficient. For example, they use less switches, but they suffer badly due to the mismatch errors. Unary architectures are less efficient. For example, they use more switches, but they suffer less due to the mismatch errors. Let's see how we calibrate the mismatch errors in the unary DACs. This is an example of calibrating unary currents. We realized this test chip in 250 nanometer CMOS technology, and this is its photo. It is about 1 square millimeter in size. The DAC resolution is 12-bit and its architecture is segmented into 6 MSB unary part and 6 LSB binary part. All MSB unary currents are calibrated. These are the distributions of the currents before calibration and after calibration. On the left is the theoretical expectation, and on the right is the actual measurement and calibration of about 1800 current sources. On-chip integrated intelligence compares every current to a common reference and adds or subtracts correction current until there is an equalization with the reference. Then the next current is taken, etc., etc. In the spectrum here we can see the harmonic distortion before and after calibration. In comparison with a DAC without calibration, having similar linearity performance, our area is greatly reduced since we can tolerate errors, use small transistors, and use on-chip intelligence. However, we rely on large unary parts of 6 MSB in our architecture, which requires a decoder and 63 slices of latches and drivers. And that's a lot. The area should be reduced further. If we want massive integration, we'll have to calibrate binary currents. This is an example of calibrating binary currents. We published the calibration method in the Upcast 2008 conference. The principle for binary currents calibration is somewhat more complicated than unary currents calibration, since we must now calibrate to an exact portion of a reference. The key to do this is to use two DAC units. First, the MSB current of unit 1 is calibrated to about the half of the reference. Then the MSB current of unit 2 is calibrated to the same level. Now both MSB currents are equal, and we calibrate these simultaneously to the reference so that both are not only equal to each other, but their sum is equal to the reference. In other words, each is equal to exactly half of the reference. In a similar way, the rest of the binary currents are calibrated. The exact algorithm steps are written here. We validated this calibration through a test chip in 180 nanometer CMOS technology. And this is its photo. It is about 0.8 square millimeters, and it contains 4 12-bit DAC units. The unit DAC resolution is 12-bit, and its architecture is segmented into 4 MSB unary and 8 LSB binary parts. All currents are calibrated, both unary and binary. Then, being able to calibrate all currents, binary and unary, we drastically reduced the area needed for a DAC unit and realized 16 12-bit DACs in one chip. All currents are calibrated, and this is the INL characteristic of a single DAC unit. In red you see the INL and the big errors before calibration, and in blue is the linearity, the INL, after the calibration. These are the output spectra before and after calibration. You see the drastic improvement of 13 dB of SFDR, which is an indication for the improved linearity after calibration. This is how the DAC units can be used in a common transfer characteristic. We have all the DAC units here named A, B, C, D, etc. And then they can be ordered in a common characteristic to achieve an effective resolution of 16 bits maximum. Now, a short video.
This is before calibration
follows
for 5.5 MHz.
The calibration.
The SFDR is around 65 dBs. Then, after executing the algorithm from the FPGA, all currents are calibrated and started to remove the harmonic distortion. And then the FDR are reduced around 79 dBs in this case.
This slide shows the DAC unit cell and how the self-calibration is implemented. For the self-calibration, three functions are needed: self-measurement, algorithm, and self-correction. Self-measurement part contains a probe transistor which brings the current to a current comparator. The current is compared against a common reference. The core of the current comparator is a single bit current sign detector that determines if the residue current flows in or out. This information is processed by the algorithm. The algorithm controls the self-correction. The correction part contains a calibrating DAC for the gain errors of the DAC units, and an individual calibrating DAC for every DAC current source. The floorplan of the DAC unit is shown in this slide. Thanks to the calibration, we can allow larger intrinsic errors and hence enjoy smooth footprints. Thanks to the calibration of the binary currents, we can allow larger binary part segmentation and hence enjoy small footprints. The area of a single DAC unit is only 0.037 square millimeters, which is one of the smallest gigahertz range DAC units. The small area allows us to integrate 16 of these units in a single test chip and hence demonstrate large-scale integration. Thanks to the calibration, the performance is not compromised. The DAC is clocked at 1 gigasample per second and maintains intermodulation distortion 3 better than minus 60 dBc up to 350 MHz. Here you can see the IMD3 sweep. The performance before and after calibration for a single DAC unit and for two DAC units combined together. To conclude my talk, I would like to repeat the main messages again. To enable the spatial dimension for wireless links, we need phased arrays and digital beamforming. However, digital beamforming is very expensive for the receiver in terms of area and power. Therefore, we need to look at hybrid beamforming alternatives. I presented to you our novel beamforming sigma delta modulator. It integrates spatial filters as feed-forward coefficients in the sigma delta loop filter. The new degree of freedom, however, is interdependent with the main parameters of the sigma delta. The complexity increases very much. We need adaptive self-learning algorithm to organize this complexity and put it in an application, like the radar. The artificial intelligence is expected to organize complexity and relax the requirements by selectively adding information in our solutions. However, it requires redundancy too. So massive arrays of data converters are very much needed. We need these for both, first, the digital beamforming, and second, the redundancy of the artificial intelligence. Next, massive arrays only make sense if they are on-chip integrated. Otherwise, the power penalty and the synchronization problems become unbearable. Therefore, we need small data converters. In the case of the transmitters, there is a challenge of combining small sizes and high performance. And here we can use again intelligence. Calibration is low-level intelligence. It reduces the needed resources without compromising performance, since it adds information into our systems. Thank you very much. If you like the presentation, please give a thumb. Otherwise, you can also always comment in the discussion below. Bye.